Here's another example where we have the f prime function is root 2x plus 1, and we want to find the area underneath that curve. In this case, we're going to start at 0 and end at 3. And so if I look at this expression with the f of x, I have root 2x plus 1 times my delta x. I sum that all up, and this gives me an approximation for the area. To make this exact, I need to then apply the limit. So I'm going to end up with this expression and then apply the limit n equals infinity, and that's going to give me the go from the sigma to the integral, which is the exact value. Okay, so let's start with the Riemann sums and see how we set this up with Riemann sums. So our delta x, we're going to need to figure out. So to figure out the delta x, it's the interval width. So in this case here, the interval width from 0 to 3 is going to be equal to 3. And then we're going to divide that by n, however many intervals we're going to use. So we're going to eventually let the n go to infinity to get the actual area, but we can use any n values to calculate Riemann sums. So we're starting with the interval equals 3, and I'm going to divide by n, and that's going to represent my delta x expression. I also need, so I'm just going to highlight that. There's my delta x here. I also need some expression for x. Again, I can see that as I move along this curve, for every interval width, each one of those, as I bump it along, that's going to be plus delta x. And I could generalize this as my next n, my n plus 1 value. Zoom in here. I can generalize this as my next n value is just based on the previous n value plus I'm just a delta x onto that. So as I bump it along, I'm going to go from 0 to 3. And since I'm starting at 0, my x coordinates are going to be starting at 0. I'm going to add a 3 over n for every k value that I add. Okay, so as I increase from k equals 1, as I add a k, I'm just going to bump it along 1 delta x. That will give me the right-hand edge of each of those rectangles. So then that expression, I can plug into my x. So this becomes 3k over n is my expression for x. My delta x needs to be in this portion here. My delta x is going to go in there, and my delta x I've already calculated as 3 over n. So I have my height of each rectangle, I have the width of each rectangle, and I'm going to sum it up as I'm going to find the different heights for every different k value all the way from 0 to the end. So just checking my values here, if I plug in n equals 1, that should give me the starting left edge of that. So n equals 1, so k equals 1, and n equals infinity. There's my n, this is my k. When k equals 1, if I'm doing this infinitely, I'm going to start at 0, and my n value is going to be when k is infinity. Again, there's my k value, and I'm going to do this infinitely, so there's my n is infinity, and I can see that those are going to cancel out, so I'm going to end up with an n value of 3 and a start value of 0. So that's going to be the same as the integral. Since I am applying a limit, this is going to be the same as the integral from 0 to 3 of the area underneath that function. Okay, and just cleaning it up from here, I can simplify some of these terms as n goes to infinity. The sum starting at k equals 1 to infinity, this is going to be the square root of 6k over n plus 1, and I'm going to multiply that by my delta x, which is 3 over n. And again, that's going to be, if I apply the limit, that will be the same as that exact value integral.